from AAA branch. Today my topic is Newton's law of cooling. Introduction to Newton's law of cooling. Newton's law of cooling describes the rate at which an object exchanges heat with its surroundings, and it states that the temperature differences between the object and the environment decreases exponentially over time. This is law is widely used in physics, engineering, and environmental science, the model cooling process. And the next point is historical background. Sir Isaac Newton first formulated the law in the late 17th century. It was developed to understand how objects reach thermal equilibrium with the air environment. The law has since been refined and applied in various scientific and industrial contexts. And here we go to mathematical expression. The law is typically expressed as fractionals and ambient temperature is a positive constant. The differential equations models how the temperature differences dimension in over time. And the next point is solution to the differential equation. Here we're gonna see that the general solution in the temperature, and here is the initial temperature of the object at the time is t equals to 0. The exponential term indicates how quickly the object approaches the ambient temperature. And now here go to factors affecting cooling rate. The value of the constant is depends on k, on the properties of the object and the environment. And next, factors such as surface area and thermal conductivity and medium can influence is k. External conditions like airflow and contact with other objects also impact the cooling process in the Newton's law of cooling. And next, practical applications. Newton's law of cooling is used in forensic science to estimate the time of death. It helps in designing cooling system and heat exchangers in engineering. The law is also applied in meteorology. The model cooling the Earth's surface is in the practical application, and the Newton's law of cooling is used in forensic science to estimate the time of the death. And next, limitation of the law. The law assumes a constant ambient temperature which may not realistic in all situations. It presumes uniform temperature distribution with the object and which is often an approximation. When these phase changes or chemical reactions occurs, the law may not accurately describe the cooling process in the limitation of the cooling. The law assumes a constant temperature which may not realistic in all the solutions. And when first the change or chemical reactions occurs, the law may not accurately describe the cooling process. And next, experimental validation. Experimental involve measure the temperature of objects over time under controlled conditions. Data from experiments can be used to estimate the cooling constant is denoted as the key. Validation helps in defining models for specific materials and environmentals. And data from experiments is as denoted in the Newton's law of cooling process is the constant is denoted by the letter of the K as a specific materials and the environmentals. And next, related concepts and extensions. Newton's law of cooling is related to the concept of exponential decay in mathematics. It can be extended to account for variable ambient temperatures and non-uniform objects. Others heat transfers modes like conductions, convections, and radiation complements the law in the complex system. It is a related concepts and extensions. Newton's law of cooling is related to the concepts of exponential decay in mathematics. And next, summary and the conclusions. Newton's law of cooling provides a simple yet powerful model for heat exchange. It is based on the exponential decrease of temperature differences in over time. Understanding the law in extension for application across science, engineering, and environmental studies. And here we go to the it is based on the exponential decreases or temperature differentiations through over time. Newton's law of cooling provides a simple yet powerful model for the heat exchange, and understanding this lies a strength of application across science, engineering, and environmental studies. Thank you.